Thank you. Thank you so much for inviting me. And I'm sorry to take time away from Aranyak's fascinating talk. So I'm going to go and switch topics a little bit, talk about an economic theory problem, and hopefully get a little bit of practical insight from it as well. This is based on two papers. One appeared at Wine last year. The other is a manuscript on the archive right now. This is work with my students, two of whom are right here in the audience, and also my ex-student Yifeng Teng, who's at Google now, and my colleague Christos Amos. Okay, so let me say what the work is about. We're going to look at a multi-buyer revenue maximization problem. So we have a seller with many items to sell, and we have many buyers with combinatorial preferences over these items. And these buyers are going to have values drawn from a known distribution each. So I'm going to think of DI as being the value distribution of buyer I. This is known. And the value of each buyer is going to be just a function that maps any subset of items to a real number. Okay. Okay, and what is a mechanism in this setting? It's going to take all of these values from the n buyers, and it's going to return an allocation, which is a partition of the items across the buyers, as well as payments that the buyers make. Okay, and of course, we assume that buyers are quasi-linear, so each buyer's objective is to maximize the value of the set they get minus the payment they make, and the seller's objective is to maximize the sum of the payments they obtain, subject to the usual incentive constraints. Okay, so that's the problem we want to solve. The input is this set of distributions. We get one for each buyer, and we want to come up with a mechanism that maximizes the seller's revenue. Now, this is known to be a notoriously challenging problem, and it's already challenging when you have just a single buyer and just two items to sell. Turns out that the revenue optimal mechanism can have a sort of unwieldy form where it's not just selling or pricing subsets of items, but it's also pricing potentially random allocations or lotteries, and it might even offer the buyer an infinitely large menu of many different choices of different lotteries. Okay, so of course, optimizing over this class of mechanisms can be challenging. When you have multiple buyers, things get even hairier because now you need to worry about externalities buyers impose upon each other. For example, if you have an item in limited supply, whom should you give it to? And in particular, the allocation and pricing that any particular buyer faces can be some inscrutable function of other people's value distributions and value functions. Okay. So the question we want to ask in this context is there a simple mechanism that will approximate the optimal one in the worst case? Okay. And to cut to the chase, the answer I'm going to give you is that as long as we are trying to approximate a suitable benchmark and under certain mild assumptions, the answer is yes. And let me be a little more specific. We're going to talk about a benchmark that I will define in a little bit. So don't worry if these terms don't make sense yet. We're going to approximate a benchmark that we call the ex ante by many benchmark, and I'll motivate why this is a good benchmark to look at. And we'll consider a simple class of mechanisms that's called sequential item pricing. What is this mechanism? Basically, it interacts with every buyer in sequence. So buyer one arrives. We're going to give an item pricing to this buyer. The buyer can choose to buy any subset of items they like based on how their values are instantiated, and they pay the sum of the prices of the items to buy this. And then the next buyer arrives, and for whatever remaining set of items we have, we're going to again come up with an item pricing. The second buyer picks their favorite bundle to buy and then walks away. And then the third buyer arrives, and so on and so forth. Okay. So we interact with the buyers in this sequential fashion. Every time we interact with the buyer, we offer just an additive or item pricing. Okay. So that's the simple mechanism. And we're going to argue that relative to this benchmark, the sequential item pricing obtains a worst case approximation. This worst case approximation, I'll go over what this is, but it depends logarithmically on the number of items available and doesn't depend on the number of buyers or the value distributions, the range of values, any of those parameters. And what's more, and this is really the key point here, is that we do need some assumptions on what kind of value functions the buyers have. So in the most general assumption we'll look at is that buyers have sub-additive values over the items. But beyond that, for these results, we don't need any assumptions on the value distributions. Okay. Okay, so that's the result I'll talk about. And but before we go into the details of the result, I'm going to place it in context because there's a long line of literature on approximation for revenue in mechanism design. And so I'll first tell you about how this result fits into that context and why we talk about the benchmark we're talking about. And then I'll tell you something about the techniques. Okay. So this question of approximating optimal mechanisms with simple mechanisms is a really, really old one in our community. And in particular, since 2007 or so, we've looked at this question of how well the simple mechanisms like the VCG mechanism and item pricing and bundle pricing, how well do these mechanisms approximate the optimal one? And the good news is that this gap is now well understood to be small, small meaning constant factor or logarithmic in the number of items within that range in many, many different settings. Okay, and there's a whole long line of work on this question. The bad news is that all of this work requires item values to be independent, meaning, for example, if you have a buyer whose value is, let's say, additive over the items, you do still need the assumption that their value of item 1 is independent of their value of item 2 and so on. And this independence is really key in how all of these results are proven. Okay, and in fact, it turns out that if we move away from this independence assumption, then provably there are no simple mechanisms that will approximate the optimal revenue in the worst case. So here's an example result of this sort. It says that the ratio between the optimal revenue and the revenue of any deterministic mechanism, one that does not sell lotteries or random allocations, can be unboundedly large. Okay, that's what I mean by the infinity there. And this holds even if you just have a single buyer and just 2 items and the buyer has additive values over the items. Okay, and so the question we want to ask is, we know that in the absence of item independence, we cannot approximate the optimal revenue. Is there anything else we can say about this setting? Okay, is there anything that will allow us to compare, for example, different simple mechanisms? Is item pricing good in that context? Do you need 2-part tariffs in order to do well? So if we just look at the class of simple mechanisms, which one has good worst case performance? This is a question we'd like to answer. And in order to answer this sort of question, a few years ago, we started to think about a different benchmark that might allow us to make statements of this sort without the independence assumption. And to motivate this benchmark, I'm going to show you this example. Here we have a single buyer with 2 items, and the buyer has the buyer's value function is equally likely to be of these 3 types. And what ends up happening in this example is that the optimal mechanism looks something like this. So you have, you're selling, the bananas at $1, the orange at $1, but if you want to, if the buyer wants to buy the bundle of these, then they need to pay $3, okay? And in effect, what happens is that the bundle costs more than the sum of the prices of the two items. And you might think of this as an exploitative mechanism. It's not the kind of thing we tend to see in practice, where, if you go on Amazon and you want to buy two different things, you're not going to have to pay, more than what you could pay for each of the items separately. Okay, and it turns out that if you see the worst case examples for optimal mechanisms, they all kind of look like this. Okay, and so this motivated asking, well, what if we disallowed mechanisms from doing this kind of super additive pricing? And we defined by many mechanisms to be mechanisms where the buyer can purchase multiple things off of a menu. Like here, the buyer could purchase the bananas for $1, the oranges for $1, and then just make up this bundle of bananas and oranges for $2 instead of $2.99. Okay, and so a by many mechanism would allow that manner of putting together different options on the menu to construct bundles. Okay, and we'll say that a menu is by many if these strategies are allowed. And so, effectively the price of this bundle will end up being $2 instead of $3. Okay, that's the idea. Okay. So these are some examples of menus that are by many and not by many. I'm just gonna say that essentially by many amounts to a kind of sub-additive pricing. When it's just a deterministic menu over deterministic allocations, it's exactly sub-additivity. When you have lotteries in the mix, it's a little more complicated than that, but you don't need to worry about it for the purposes of this talk. Okay. And so now we can define by many revenue as being the optimal revenue over by many menus. And the new question we want to ask is, can we approximate by many revenue? Okay. And so I told you why, I told you sort of, one reason one might think of optimal mechanisms for worst case examples as being exploitative or not reasonable in certain ways. But really one reason that we want to study by many mechanisms is this new benchmark gives us a way of saying something about the performance of simple mechanisms that we didn't get before from the optimal revenue benchmark. Okay, so it turns out that for a single buyer setting, if you have a single buyer with a combinatorial value function, it turns out that there's a simple mechanism that always approximates the optimal by many revenue for this buyer within a factor that's logarithmic in the number of items, and no matter what the value distribution of the buyer is. Okay, so all we need to say is that there are M items for sale, and item pricing approximates the optimal by many revenue for this buyer. Okay. And it also turns out that this result is in fact tight in that there's no other mechanism that has small description complexity that will do any better than logarithmic in the worst case relative to this benchmark. Okay, so in that sense, this gives us a nice answer for what happens when you go beyond the item independence assumption for a single buyer. And subsequently, there were some other results showing nice properties of by many mechanisms, but all of this work was for a single buyer. And what I want to talk about today and the new work is about extending this sort of benchmark and this concept to settings with multiple buyers. Okay. Okay. So in the rest of the talk, I'm going to motivate an extension of this by many benchmark to multiple buyers, and then I'll tell you about the results relative to this benchmark. Any questions?
So
yeah.
It's still in the valuations are still independent across buyers.
Yes, the valuations are independent across buyers. Yes.
just a clarification, if we allow approximation, how does the menu complexity scale with that? So even if it's better than log n, then you still need a large menu, is what you were saying?
Yes, so you do need large menu complexity if you want something better than log n. Yes, yes. So you need exponentially large menu complexity. Yeah, but there are some results on menu complexity that we can talk about offline. Yeah. Okay, so let's talk about the multiple buyer setting. And it turns out that things get a little bit complicated with multiple buyers. And to explain this, I want to think about the by many constraint on these mechanisms in two different ways. So you can think of the by many constraint as a strengthening of the buyer's power. So this time around, the buyer is allowed to purchase multiple things off of the menu. The buyer is allowed to interact with the mechanism multiple times, and that gives them a bigger space of strategies and therefore more power. We can also think of this alternately as a weakening of the seller's power. So the seller is now constrained to offering these sub-additive pricings, and so there's the space of menus the seller can optimize over is small. Okay, and it turns out that in a single buyer context where you have essentially, we're thinking of unlimited supplies, there are no supply constraints on the seller's end. These two interpretations are essentially the same, because when you have unlimited supply, the seller so for every subsequent interaction with the buyer, the seller really just offers the same optimal menu. And so you can really think of these as effectively the same kind of constraint on the mechanism, on the space of mechanism. But in the case of limited supply, which is the kind of setting we encounter when we're talking about multiple buyers, so buyers are imposing externality on each other precisely because supply is limited and we can't allocate the same item to multiple buyers. And in this case, it turns out that these two approaches are different because, in particular, the seller can now change the menu it offers to a buyer between different interactions as the supply changes. So here's an example. So let's say we have an item to sell, and on the first day, we offer to sell the item to buyer one at $3. And then we say, well, if the buyer refuses to buy the item at $3, we're going to offer it to another buyer. And this other buyer will purchase the item with 50% probability. And so from buyer one's perspective, if they give up on the $3 price tag, then they don't have another opportunity to get the item with more than 50% probability. Okay, but if the second buyer also rejects the item, then the first buyer can come back and purchase the item at a discount. Okay, but effectively what happens is if we think of this as, if we think about this mechanism in terms of the kind of menu that's offered to the first buyer, okay, this is like a menu that sells the item with certainty at $3 and sells the item, a lottery ticket with 1/2 probability of getting the item at $1. This is not a by many menu. It's not it doesn't satisfy the sub-additivity property. And so here, the seller is using this threat of allocating the item to the second buyer as a means to implement a non-sub-additive pricing for buyer one. Okay, and effectively, what this means is, this interpretation of allowing the buyer to interact with the menu multiple times provides us no strengthening in the multi-buyer setting over the original optimum. Yeah. It might be a nice notion to want to think about, but from the viewpoint of a benchmark that will allow us to understand which mechanisms perform well for these multi-buyer settings, it's not a very effective benchmark. So we'll focus on the second approach, which is limiting the seller's power directly in order to come up with a reasonable benchmark. Okay. So let me say how we can do that. What we're going to do is we're going to think of the seller as, we're going to think of the interaction the seller has with every buyer individually, and we're going to use that as a basis of defining this weakened space of mechanisms the seller is allowed to offer. And there are different ways in which a mechanism can interact with each buyer individually. So here's one approach. The seller is going to interact with every buyer in sequence. And so for the first buyer, the seller offers a buy many menu. The buyer purchases some set. And then the seller goes to the next buyer, offers a buy many menu, and the buyer purchases a set, and so on. Okay, so you could imagine one extension of a single buyer by many mechanisms to multiple buyers in the sequential fashion. A different approach you could use is to say, well, I'm going to run a direct mechanism. So the buyers report their valuations, and the seller is going to just return an allocation and a pricing to each of them. And the pair of allocation and pricing must satisfy the property that if I fix the value V2 of the second buyer and I look at the menu, effective menu that's offered to the first buyer as a function of their valuation, this should be a buy many menu. And this should happen for every valuation of the second buyer. And same for the second buyer here. For every possible choice of V1, the menu I offer to buyer 2 should be a buy many menu. Okay. Now, these two are very different ways of extending a single buyer buy many mechanism to multiple buyers. So these are not all. You could ask the seller to run a direct mechanism where the ex ante pricing, effective ex ante pricing offered to every buyer is a buy many pricing, and so on. There are different ways that you could extend this. And these are all slightly different. And so you might ask, well, what basis do we have of choosing one versus the other? So we're going to sidestep this entire question. And instead, I'm going to tell you about a relaxation of buy many revenue that's going to capture each of these different mechanisms. In the sense that if I optimize over this relaxation, then this is going to be at least as good as any of the classes of mechanisms I described on the previous slide. Okay, and what is this relaxation? It's called an ex ante relaxation, and the idea is that we're gonna, separate out this externality across different buyers through an ex ante supply constraint. Okay, so let me be more precise. We're gonna use Xij to denote the probability with which a mechanism tries to offer item J to buyer I, allocates item J to buyer I. And of course, these probabilities, these are probabilities over all the instantiations of the value functions. And of course, they should satisfy the property that each item is sold at most once, okay, in aggregate. So this constraint, of course, if this is a constraint in expectation over the instantiations of the value functions, it's an ex ante constraint. I'm not enforcing it ex post, I'm only enforcing it ex ante. And the ex ante by many optimum is simply going to be the best way of coming up with these ex ante feasible allocations, where now for each buyer I'm going to look at how much I'm supposed to allocate to this buyer, and I'm going to find the best way of allocating to this buyer under that constraint. Okay, so let me read through this. a little bit. So I'm going to say that a single buyer mechanism, so now I'm thinking of one buyer, buyer I, and this mechanism is going to satisfy some given ex-ante constraint if it's the case that when I draw the value of this buyer from their distribution, the probability that I allocate item J is no more than what's given by the ex-ante constraint. Okay. And now I can define for a single buyer, given an ex-ante constraint, I can look at all possible by many mechanisms that satisfy this constraint over all items, and then I can take the one that has the most revenue. Okay. And if I sum up these revenues over all buyers and take the best possible sequence of vectors xi that maximizes this, that gives me this ex-ante relaxation over by many revenue. Okay, so again, what we've done is we've said, well, let's figure out the probabilities with which I want to give the items to every buyer. These probabilities should satisfy the ex-ante supply constraint. And now, given these probabilities, I can go look at every buyer independently and ask, what by many menu should I offer to this buyer to maximize my revenue? Okay, and of course, this is not a feasible mechanism because if I tried to run this, some of the times I'd be over allocating items, and that's not feasible. Okay, so this is just a relaxation, but it gives us an upper bound on what any multi-buyer by many mechanism can do here. Yeah, and so this is the relaxation we want to approximate. Okay. And so our main result will be to argue that this ex-ante by many relaxation is approximable via sequential item pricings. And in order to do this, we're going to use an intermediate quantity that we'll call the ex-ante item pricing optimum. What is this? This is essentially, again, an ex-ante relaxation, but where every individual mechanism for every individual buyer is required to be an item pricing. And this is just going to be a tool for us to argue that the benchmark over here is approximable using the mechanism over here. Okay, so we're gonna, so our argument has two parts. First, we're gonna argue that this ex-ante by many approximation is in fact not too far from the ex-ante item pricing optimum. Okay, and second, this ex-ante item pricing optimum can be essentially rounded into a sequential item pricing. Okay, so again, what an ex-ante item pricing optimum does is it finds the best way of coming up with ex-ante allocations to the different buyers, probabilities for allocating items to buyers so that they satisfy the ex-ante supply constraint. And then it just looks at every buyer alone and asks, what's the revenue optimal item pricing I can offer that satisfies these supply constraints per buyer. Okay. And on the one hand, this item pricing benchmark approximates the by many ex-ante benchmark. And on the other hand, this can be rounded off into a sequential item pricing. Okay. Any questions? Okay, so I'm going to tell you about the two technical components in slightly more detail now. Okay. So first of all, I'm going to argue that the by many revenue we get for the ex-ante relaxation is approximable using an item pricing. Okay, so what does this entail? So now we're just focusing on a single buyer. the single buyer has a value drawn from some distribution. And furthermore, we have some ex-ante constraint. This just tells us, every item is to be sold to this buyer with some probability bound on it. Okay, and so we want to make sure that the mechanism we offer satisfies those probabilities of allocation. Okay, and on the left-hand side, we have by many revenue here. So this is some mechanism that satisfies these ex-ante constraints xi. And on the right-hand side, we have the same thing, but with item pricing. So we want to argue that by many mechanisms are not much better than just item pricings that are additive. And you can think of this as basically saying, sub-additive pricings can be approximated in revenue by additive pricings. And this is what the single buyer result basically said before. So you can think of this single buyer result that I talked about earlier as being essentially the same result, except now the ex-ante constraint is just 1 everywhere. You're allowed to allocate every item with probability 1 to the buyer. Okay. So one way we might, this is just a rephrasing of this result. It says that, in fact, for any fixed valuation, for any by many mechanism M, I can come up with a random item pricing such that for any fixed valuation, the expected revenue of this item pricing is within a log M factor of the revenue of the mechanism. Okay, that's what the previous work says. And the problem with that previous work is that it comes up with this random item pricing, but it has no way of controlling what this pricing is going to allocate. The mechanism might be allocating something, the pricing might allocate something entirely different. And so there's no direct control over these how the allocations change when we go from the mechanism to the pricing. And one way we might try to deal with this ex-ante constraint is to say that, well, let's Lagrangeify this constraint. And what does that look like? We're going to basically come up with some appropriate cost vector here and think of this as a profit maximization problem where the seller has to pay a particular cost for every item it allocates, and now we want to maximize this difference of revenue and cost. Okay, and so this cost vector is basically the Lagrangian form of the allocation constraint. Okay, and then you might hope to prove essentially this theorem for profit instead of revenue with respect to this cost vector that appears magically from somewhere. Okay, and we might ask, is this true now? Okay, and it turns out that this is not true because in the presence of costs, sometimes when the costs are very high and close to the buyer's value, by just selling the buyer the right kind of lottery, the by many mechanism can do very well, whereas an item pricing might not be able to exploit those small gaps. So this is simply not true, but it turns out that we can do a slightly different version of this, and we can penalize the by many mechanism a little bit and show that for any cost vector C, there's some random item pricing, which if it faces smaller costs relative to the mechanism M, then it can recover a good fraction of the profit of M. Okay, and I won't say how we do this. It's more or less the same kind of approach that the previous work used. So I won't go into the details, but this is a way of showing how an ex-ante item pricing is close to an ex-ante by many mechanism. Okay, so that's the first step of our process. Now I want to go to the second part. The second part says that we have some ex-ante allocation constraints, and we have this benchmark where we have a sequence of item pricings that satisfy the ex-ante probabilities. Now we want to implement the same thing using a sequential item pricing that satisfies the supply constraints ex post. So I don't want to oversell any items, okay? And the approach we use to prove this kind of a theorem is what's called an online contention resolution scheme. This has been studied extensively in the context of social welfare maximization and profit inequalities. And what it is, and it's also been studied in the context of online algorithms in various settings. And what it is a sort of online rounding scheme. And let me just describe it in this sort of single dimensional context. So let's suppose that we just have a single item to sell, and we again have n buyers, and now we're given these ex-ante allocation probabilities, xi, and they sum up to 1 because we only have a single item to sell. And so the optimum, the ex-ante optimum, sells to buyer I with probability xi, okay? And we want to make sure that somehow we're trying to figure out in an online fashion, one buyer at a time, whether or not to allocate to a buyer. And we want to make sure that when we get to buyer I, we're going to allocate to this buyer with probability roughly equal to xi. Okay, so how do we make this happen? Well, we just need to make sure that when we get to buyer I, we have the item available with some high enough probability, because if so, then we can allocate to this buyer. But if the buyer gets blocked by someone else getting allocated before them, then we're in trouble. Okay, so here's a simple 1/4 OCRS that one can show. What you do is when you get to buyer I, you're going to allocate to them with probability exactly xi/2. Okay, and so with these probabilities, when we get to some particular buyer I, or in fact, even at the end of the process, the probability that we allocated to anybody at all is going to be at most the sum of these xi/2s, which is at most 1/2, given our ex-ante supply constraint. And so with 1/2 probability, we don't sell the item, which means that when we get to buyer I, this buyer is unblocked with probability 1/2. We're going to sell to them with probability xi/4. So I'm sorry, xi/2. So the net probability that the buyer gets the item is xi/4. Okay. And from the viewpoint of social welfare, this is already going to give a 4 approximation because we're going to sell to the xi/4 highest quantiles of this buyer. But in fact, in single parameter settings, this also gives an approximation to revenue, because you can you're going to get a revenue at least a quarter of the revenue a mechanism selling with probability xi would get. This is because the revenue function is a concave function. Okay, so that's great. And really the key thing here was we want these selling probabilities to be not too large and not too small relative to xi. Okay. What about the multidimensional setting? We want to again do something like this, something similar. We have these probabilities xij, probability of selling item j to buyer I. When buyer I arrives, we want to make sure that the allocation to this buyer is some constant times xi. Okay. And then we might hope, well, because the revenue function is concave, we can make this alpha approximation to revenue. Of course, the challenge is that these allocations now are not allowed to be completely arbitrary, but rather we need to come up with some item pricing, and then the buyer is going to make some choice, and we need to respect these choices. And so the allocations are going to be given by those choices. So they're not allowed to be completely arbitrary. And furthermore, the revenue function is concave, but that doesn't allow us to compare sort of the revenue at some vector of allocations to the revenue at some other arbitrary vector of allocations. So it doesn't quite work out that way. So to be more precise, this is formally a statement of the kind of lemma we want to prove. When buyer I arrives, and when we're given these ex ante allocation probabilities xi, and let's say we're also given the pricing PI that achieves the optimal ex ante item pricing revenue that satisfies xi. And furthermore, after having gone through buyers 1 through I minus 1 and having sold some subset of the items, we're left over with some set of remaining items. Let's call those Ri. And what we want to do is to come up with some pricing Qi such that the expected allocation of Qi, my pointer is not working, but the expected allocation of the pricing Qi over the set of remaining items and over the randomness in the buyer's valuation is not much larger than xi. And furthermore, the revenue of this pricing is comparable to the revenue of pi. So that's formally the lemma we want to prove. And of course, in order to prove this, we need it to be the case. Oops. So we need it to be the case that this random set Ri contains enough items. Okay. And as long as we make sure that we're not over allocating items to the buyer, so this alpha 1 here is some constant smaller than 1, we can make sure that every item belongs to the set Ri with some constant probability. Okay. And so that's what goes into proving this OCRS. Okay, so let me just, because we're also out of time. So let me just wrap up. So this is the kind of statement we want to prove, and it turns out that the kind of factors we can achieve here depend very much on what classes of valuations the buyer is allowed to have. So in particular, if the buyer has unit demand valuations or additive valuations or cross substitute valuations, we can prove an OCRS of this sort that gets a factor of 2 approximation to revenue. And this is in fact tight because it's this problem generalizes the single item profit inequality for which 2 is tight. When we go beyond those kinds of cross substitute type of valuations, we can show that when the buyer has sub-additive valuations, then we get an OCRS that is logarithmic in the number of items. And turns out that this is almost tight even for XOS valuations. So there's a square root log m lower bound. And all of this put together with the fact that ex ante item pricing revenue approximates ex ante by many revenue, we get polylogarithmic approximations in the number of items. And I want to emphasize that the approximation factors depend only on the number of items and not the number of buyers. And one final word, it's too bad that my screen is not working. But one final word is that it's worthwhile kind of comparing the results we achieve to similar results that have been achieved in the setting with item independence. So when buyers have sub-additive values, but the values for individual items are independent, it is similarly known that sequential 2-part tariffs in that case approximate the optimal revenue. So the difference is that here we don't have the independence assumption, but we approximate a weaker benchmark. But the interesting aspect is that the mechanism that in the end turns out to be approximately optimal is almost much the same in the 2 cases. And also in all of these different scenarios, turns out that sequential item pricing does just as well as any simple mechanism can do in these contexts from the viewpoint of worst case approximation. And so sort of a practitioner's takeaway to this is, if you care about worst case approximation to revenue, you might as well just focus on optimizing over item pricings or sequential item pricings, and there's no need to look beyond. Okay, so that's sort of my final message. Thank you. Yeah.
I guess, bidder independence is necessary, or like
yes, bidder independence is absolutely
just to talk about it, like ex ante relaxation and so on.
Yes, yeah. Yes, because,
You guys get, okay.
yeah. Yeah, because you do need independence between the set of remaining items and the value that's drawn. I don't know if what might happen if those two are correlated. So yes, just for this lemma, you do need those two quantities to be independent. Yeah. But I think it would be interesting. So there, there are lots of different techniques for looking at correlated values under item independence. So maybe some of those would apply here too. Definitely an interesting direction.